In this module, we will talk about a baseline model in case of classification. So we have talked about baseline models in regression. Let us talk about baseline model in case of a classification. Quick recap. What is a baseline model in regression? A baseline model in regression always predicts the average of the dependent variable. So it predicts the average of the dependent variable. Now let us see what a baseline model predicts in case of classification. So let's say for an example, your dependent variable comprises of 60 zeros or 60 no cases. Again, we are talking about a binary classification case, and I have 40 ones or 40 yeses in my data. So this is how my dependent variable comprises of. Now what would a baseline model predict in this case? In this case, a baseline model will predict the mode. So a baseline model in this case will predict mode. What does it mean? This means that for all the 100 records, so total we have 100 records. So for all the 100 records, a baseline model will predict 0. So 0 will be the prediction for all the 100 records. Now out of all the 100 predictions, 60 of them will be correct, as 60 are actual zeros. The rest 40 would be wrong. So if we calculate the accuracy of such a model, the accuracy of a baseline model, we would get 60% as the accuracy. So baseline models are used to come up with a better model. So as you can see here, even by just predicting 0 for all the records, we are still getting an accuracy of 60%. So this is like random guessing. Since I have more zeros in my data, a baseline model will predict 0. So why did it predict 0? Because I had a greater proportion of 0. I had 60 zeros in my data compared to only 40 ones. So baseline model predicts that class which is more in proportion in the data. Now let us compute a confusion matrix for this baseline model and see how it performs. So I'll again write the actual values on the left hand side, actual zeros and ones, and I will write the predicted values on the right hand side. So predicted zeros and ones. This is my confusion matrix for a baseline model. So a baseline model in this case is not predicting any 1. So my prediction 1 will be 0. So my false positive and my true positive, both of them will be 0. And what about my true negative and false negative? Let us see. My true negative would be 60. My true negative will get a count of 60. Why 60? You can see there are 60 zeros here, and a baseline model predicts all hundreds are zeros. So obviously 60 of them will be matching. So I have written here 60. And here we will have the remaining 40. So baseline model predicts 100 zeros. So 60 of them will be true negative and 40 of them will be false negatives. So this is how it would look like, a confusion matrix for a baseline model. Now from here, if you compute the accuracy, you would get 60%. So accuracy, remember, is the sum of the diagonal terms this way. So we would get 60% as the accuracy. And if you calculate the error parameter, we would take the opposite diagonal this time and you would get an error of 40%. So this is how a baseline model would do. A baseline model is a very crude model which just predicts the class which is more in proportion. In this data, zeros are more in proportion. Now let us see another scenario, a scenario of unbalanced classes. So this is known as the unbalanced class. So unbalanced class is where you have a high proportion of one of the classes and a very low proportion of the other. So this typically happens in some cases. So for example, a rare disease, a very rare disease which happens only in 1% out of 99, let's say. So if we write this 1 as a 1, the occurrence of the disease as a 1 and the non-occurrence of the disease as a 0, you would get 1 this is the class, and this is the count. You would get only one count of the class 1, and you would get 99 counts of the class 0. So this is a very rare disease which happens in one individual out of 100. So this is how it would look like. Let us see how would a baseline model perform in this case. So let's calculate the accuracy of a baseline model for this example. So in this case also a baseline model would predict 0 always, since zeros are more in proportion. A baseline model in this case would predict 0. So the accuracy will be, it's very clear, the accuracy would be 99%. For 99 of the data, it will make a correct prediction. Only for this one particular data point, the prediction of a baseline model will be wrong, because it would predict, so if I write the prediction here, it would predict 0 for this particular record, whereas it was actually a 1. But for all these 99 also it will predict a 0, and these will be correct. So the accuracy will be 99% and the error will be 1%. Now you can clearly see that this kind of a model will not be useful for us. Neither will the accuracy will be useful. So the accuracy as well is deceiving as a parameter, because a person looking at the accuracy would think that he has a very good model available which is giving him or her accuracy of 99%. But if you look at the data, you would see that this is not a good model, because just one person had the disease and the model failed to identify that person. So in these cases, we do not use accuracy as the evaluation parameter. We have a few other parameters which we'll talk about in this video, and those parameters become very important, especially in case of unbalanced classes where you have more of one class and less of the other. Also, it depends on your business requirement. So for example, in this case, if your goal is to identify that person, the person who has the disease, the person might be very few out of a lot of people. Very few people might have the disease. So your goal of building a model is to identify those few individuals. So your goal is to identify the ones in your data. So whereas the accuracy gives equal weightage to both ones and zeros. So remember, the accuracy is a sum of true positive and true negative divided by total. Now accuracy gives equal weightage to both true positive and true negative. So even if your true negatives are high in number, you would get a very good accuracy, but sometimes the business requirement is to identify the true positives. So in this case, the person who has the disease is a true positive. If you predict 1 for him, he would be the positive person, and that is your goal. Your goal is to identify that person who has the disease. You're not concerned with identifying the people who do not have the disease, but your goal as an analyst, as a data scientist, would be to identify those few records in your data who are ones. So in this case, we resort to another parameter which is known as sensitivity. So we evaluate such a model in such cases by the sensitivity. This is also known as recall. So what is this parameter? This is the true positive rate. So this is the true positive rate. So how do we calculate the true positive rate? This is given by true positive divided by true positive plus the false negative. So this is the formula which is used for calculating sensitivity or recall. So remember from your confusion matrix, this is our confusion matrix. So we take the true positives, from here, and then we divide it by the row total. So we are dividing it by the row total. What is the row total? The row total is true positive plus false negative. So that's what I have given here. I have taken the entire row here, and that is the denominator. So remember this confusion matrix, and you are dividing it by the entire row. So this is how you calculate sensitivity and recall. Now what is the interpretation of this parameter? What is the interpretation of sensitivity or recall? So the interpretation is this entire parameter represents your actual ones. This represents your actual ones in your data. If you look at the confusion matrix, you will see this entire row represents the actual ones. This represents the actual ones in your data. So sensitivity or recall or true positive rate measures how many ones are you identifying out of the total actual ones. So remember, true positive is where the actual is 1 and you predict also 1. So this is your accuracy parameter. This is something good for you. So sensitivity measures how many ones are you correctly identifying out of the total actual ones. So this is a very important parameter which gives emphasis only to identifying ones. So you see there is only true positive as the numerator, so it only values how good is the model identifying the ones and does not consider the zeros. The accuracy parameter considered the zeros also, but here we have only true positive. So it considers how well is a model identifying the true positives in your data, or how well is the model identifying the ones in your data. So let us calculate the sensitivity or recall for the baseline model. So we have the baseline model here. So we have already computed the confusion matrix for the baseline model. Let us quickly compute the sensitivity for this. So the sensitivity would be true positive divided by true positive plus false negative. So the true positive, what is the true positive for us? It is 0. So the numerator will be 0, reducing the entire term to be 0. So the true positive for a baseline model for this data would be 0. So this shows how important sensitivity as a parameter is. We saw that in such a case where you have 40 observations as ones and 60 observations as 0, and you go by a baseline model which always predicts 0, it is basically a model which is useless to you because you're not able to identify even a single ones in your data. So sensitivity would be a better parameter to evaluate such a model, and in this case it would be 0 because the model will not catch any ones in your data. Similarly, we have another parameter called specificity. So specificity is opposite of sensitivity. This measures only the ones. It gives emphasis only on the ones, only on the zeros, sorry. So this measures only the zeros. So in this case, instead of true positive, we will have true negative, and in the denominator again you will have true negative plus false positive. So going back to the confusion matrix, the specificity will be true negative, which is this parameter, divided by once again the row total. So this is the row total. So the row total is true negative plus false positive. That's what I have written here. So the interpretation of specificity is it measures how well is your model identifying the zeros out of all total zeros, out of all actual zeros in your data. So at the denominator you have the actual zeros, and at the numerator you have the zeros which the model was able to identify. So specificity measures how good is your model doing with respect to the actual zeros, and it only gives emphasis on the zeros. Sensitivity, on the other hand, only gives emphasis on identifying ones. It does not care how good or bad you are doing for the zeros, and similarly specificity only cares about the zeros. So two different parameters depending on whether you want to identify the ones in your data or you want to identify the zeros in your data. If you want to identify both of them, if you want to give equal importance to identifying both ones and zeros, we use the accuracy parameter which we have seen earlier. Now there is one more thing that has to be discussed with respect to the different parameters that are used, which is the precision. So let us see what is a precision. Now let's say your goal is to identify the ones in your data. So if your goal is to identify the ones in your data, the parameter that you would be looking at is sensitivity, we just discussed. So we will be looking at sensitivity as the parameter and we will try to increase sensitivity to as high as possible. So we will try to make sensitivity 100% or 1. Now to do that, you might predict all the data points as 1. So one solution to increase sensitivity would be to predict all the points as being a 1. For example, if you know that out of 100 people, one person has a disease and you want at any cost to identify that person, what would you do? You will not predict all person as not having the disease. That would be a baseline model, and we saw that would have a sensitivity of 0. You will never catch that person. So if you want at any cost to catch that person, one way would be to predict that all 100 of them have the disease. So if you predict all 100 of them have the disease, you will definitely catch that one person who actually has the disease. But this would be a very lame model which predicts all are 1, and it will not be practical business wise. So imagine a hospital predicting all the patients would visit the hospital to have cancer just to identify that particular cancer patient. This would be very impractical and probably unethical as well. So to control that, to put a control on that, we have the parameter called precision. So precision helps you avoid predicting all the observations as 1. So how is this measured? Let us look at it. So precision, the formula for that is true positive divided by true positive plus false positive. So in this case, at the denominator you have the row total. You don't have the you have the column total, sorry. You have the column total as the denominator and not the row total. So true positive plus false positive, you can see here it is the column. It is this particular column that I have given as denominator. So what is the interpretation of precision? The interpretation is that it measures out of all predicted ones, how many are actual ones. So you can see the denominator is all predicted ones. So this is the denominator, the sum of the column sum, which is the predicted one. This column is all predicted ones. So I have written it measures out of all predicted ones, how many are actual ones. So the true positive measures the actual ones. So out of all total predicted ones, how many are actual ones. Now if you blindly predict everybody to be 1, then your precision will be very low because only a few people out of everybody will be actual ones. So your precision will fall drastically if you are blindly predicting everybody to be a 1. So for this example in case, let's calculate the precision for this example. Our true positive is 0 here. So our true positive is 0. So in this case it will be 0. It's a baseline model. So let us predict all 100 to be 1s. So if all 100 are 1s, so this is actual, this is predicted, so 0 and 1. So if we predict that all 100s are 1s, we will have only 1 as the true positive because only one person has the disease. So this is the actual data where we have 99 zeros and 1 we have, and this phenomenon, this term will be 99. So our false positive will be 99. 0 we are not predicting any, so it will be 0. So let's calculate the precision for this. So the precision would be true positive, which is 1 divided by total, which is 100. So it would be a very small 1%. So predicting 1 for everybody just to identify that particular guy who is a 1 will give you a very bad precision. So we will avoid doing this. If we had only looked at sensitivity in this case, we would have gotten 100%. So the sensitivity for this data will be 100% because it will measure 1 divided by the row total, which is 0 plus 1, so you would get 100%. So ideally when you are focusing on identifying the ones correctly, you should not just focus on sensitivity, you should focus on sensitivity and precision, both of them. If you start blindly predicting too many ones, then your sensitivity will increase but your precision will fall down. But if you are judiciously predicting ones and they are turning out to be actual ones, then both sensitivity and precision will be high. So using these parameters, we evaluate a model based on the business requirements. If the business requirement is to identify ones, we measure sensitivity and precision together. If the business requirement is to identify both ones and zeros, we usually measure accuracy. In a further video, we will see another parameter that is used to evaluate a model.